Welcome back to my astronomy series. Today we're going to be calculating Earth's orbital velocity, and if we have enough time, maybe we'll sneak in calculating the mass of the sun. So this will allow us to move further down this ladder of extrapolated information. So let's dive right in. We are going to start by drawing the sun. Oh geez. Oh geez. And we're going to draw the orbit of Earth around the sun. Maybe I should have chosen different colors. Don't read too much into this. And we'll draw a little Earth. Aw, that's so cute. Okay. Again, all orbits are going to be simplified down to perfect circles, just for demonstration purposes. If Earth's motion is described by this orbit, then we can actually calculate its acceleration. How? Well, we can calculate its acceleration because we are assuming a perfectly circular orbit. And having a perfectly circular orbit means that Earth's acceleration is just its centripetal acceleration. So we can write out the formula for centripetal acceleration, which is A equals v squared over r, where v is going to be the velocity of Earth in orbit, and r, you know what? Let's change out these colors. Let's make this like green for v. I am so sorry. That looks horrible. And orange for r. And r is going to be the distance from Earth to the sun. Why is it the distance from the Earth to the sun? Is because, again, the centripetal acceleration takes the radius of the circle. And if our orbit is our circle, then we know that the radius is going to be Earth, and it's orbiting the sun, which means that the sun is in the center of that circle. So that r is just going to be the distance from Earth to the center of the sun. Cool, we now have a way to calculate Earth's acceleration in its orbit. Nice. But how does that even help us? And what are we even doing with that? Well, let's take a look at everything we've learned and then go from there. So let's lay out what we know and start there. In the first video, we talked about Newton's law of universal gravitation, which is the force of gravity is equal to the gravitational constant times mass 1, times mass 1 times mass 2 over r squared. Thanks, Newton. We also know of Newton's law of motion. And what is Newton's law of motion? It states that force is equal to mass times acceleration. Okay, well, we're starting to see something somewhat similar here. So let's do one thing at a time. What if in Newton's law of motion, we set this mass equal to the mass of Earth? So we can substitute that out one at a time. Let's say F equals, and then we're going to use blue for the mass of the Earth, and then times acceleration. All right, cool. But wait a second, we know that A in Earth's orbit, its acceleration is due to its centripetal acceleration, and we know that centripetal acceleration is A is equal to v squared over r. So let's replace this A with what A is equal to up here. So now we can write force equals mass of the Earth times acceleration, which is equal to v squared over r squared. So let's take this green. We go v squared over r. Newton's law of universal gravitation, which we used this last time to calculate the gravitational force between Earth and the sun. As we just discussed, centripetal acceleration, A, can be calculated just by taking the speed squared divided by the radius of the circle. And the radius of the circle is just the distance from Earth to the center of the sun, since we are orbiting around this sun in a perfect circle. Nice. Okay, cool. So now, simply by using Newton's law of motion, completely avoiding Newton's law of universal gravitation, we can find the force of gravity on Earth due to its motion without even using Newton's law of universal gravitation. Thanks, Newton. So we're going to pause here and talk about Earth's orbital speed. To be able to calculate this speed, as we just saw, we need to know the radius of the circle, aka the distance from Earth to the sun. I'm just going to give you this distance right now, but in future videos, as we move farther down this ladder of extrapolated information, we're going to actually calculate this distance. So there's something to look forward to, I guess. So let's come back up here. And like I said, I'm just going to give you r. And r, the distance from Earth to the sun, is equal to 1.5 times 10 to the 8th kilometers. And we're going to pause here again to talk about this distance. I'm sure you're already seeing this problem or in past videos, or you're slightly annoyed by this problem but haven't been able to pinpoint precisely what's annoying you. I'll give you a hint. It's 1.5 times 10 to the 8th kilometers. That's a huge number. That's like an extreme distance. How do we even wrap our heads around that type of distance? Well, let's start here. Let's say that you're going to go on a road trip to the sun. Maybe it's a little vacation. I don't know. Bear with me. So if you want to take a vacation to the sun, you're going to need to drive 1.5 times 10 to the 8th kilometers, which is the radius of our circle, the distance from Earth to the sun. So in the US, the average highway speed's around 70 miles per hour, which I believe is around 110 kilometers per hour, if I'm not mistaken. So the question becomes, how long would it take you to drive 1.5 times 10 to the 8th kilometers, the distance from Earth to the sun, moving at 70 miles per hour, or 110 kilometers per hour? Yeah, just a breezy 163 years to get to your destination. Yeah, you can speed if you want, and crank that up to 120 miles per hour. You're still going to be around 100 years to get to the sun. Thanks, Newton. So if these are the distances that we are going to be working with from this point forward in astronomy, then it might be better to find and use different units other than just kilometers or miles, because I don't want to have to say 1.5 times 10 to the 32nd kilometers, right? What does that mean? We need a new unit with a crazy cool name so we can better comprehend these astronomical distances. I'm pretty sure that's exactly how it went down. So anyways, at the end of that conversation, they came to a conclusion, introducing the most unique name for a unit of all time, the astronomical unit. Woo! 1 AU, 1 astronomical unit, is equal to 1.5 times 10 to the 8th kilometers, aka the average distance from Earth to the sun. Pretty convenient. Okay, but anyways, back to calculating the speed of Earth in orbit. So we know r now. R equals 1.5 times 10 to the 8th kilometers, or 1 astronomical unit, 1 AU. See how much better that is? And if we pretend Earth follows this perfect circular orbit, then the distance from Earth to the sun is simply the radius of this circle, of this orbit that we talked about. To calculate speed, we need to know two things. We need to know the total distance traveled, as well as how long it took you to travel that distance. So the total distance traveled, we can say, is going to be 1 full revolution around the sun. 1 full orbit is going to be the total distance. And we can find this total distance just by calculating the circumference of a circle, because this orbit is going to be our perfect circle, and we know that circumference is equal to 2 pi r, where r is the radius, and we know r. Okay, so we now know a way to calculate the total distance traveled, but what about the total time? How long it took us to travel that distance? Don't overthink it. If the total distance is 1 full revolution around the sun, and starting and stopping in the same spot, then the time it took to travel that distance is, 1 year, aka the literal definition for the word year. Nice. Again, we know that the speed is equal to the total distance, so distance over the time it took you to travel that distance, right? Also known as the change in your distance, we're going to use x for distance here, over the change in time. So if this is how we calculate our velocity, we know our total distance will be 2 pi times r, which r is 1.5 times 10 to the 8th kilometers over the time it took us to travel that distance, which is 1 year. So our orbital velocity is 2 pi times 1.5 times 10 to the 8th kilometers per year. Yeah, those units aren't helpful at all. So let's actually simplify these units to being kilometers per hour so we can better gauge how fast Earth is actually moving. So to do that, we can just simplify out the top by doing this calculation. So let's bring over Desmos and let's do 2 times pi times 1.5 times 10 raised to the 8th, which is approximately 9.42 times 10 to the 8th kilometers per year. Okay, but now we need to convert years into hours. And that's pretty simple. All we have to do is figure out how many hours are in 1 year, which can be done by saying in 1 year, we know that there are 365 days. And in 1 day, we know there are 24 hours. So the days cancel out, and this leaves us with, in 1 year, there are 365 times 24 hours, which again simplifies down even further to being 365 times 24, 8,760. There are 8,760 hours in 1 year. So now if we come back over here, we can say velocity is equal to 9.42 times 10 to the 8th kilometers over, in 1 year, we can substitute out 1 year for 8,760 hours. And this will give us our orbital velocity of 9.42 times 10 raised to the 8th divided by 8,760. It gives us 107,534. So roughly 100,000 kilometers per hour. Or what's that? Like 70,000-ish miles per hour. This is the orbital speed of Earth. This is how fast we are moving around the sun. Yeah, personally, I'd classify that in the pretty fast category.